how many of you know how much time it takes you to get to work or school? How many of you know that you can jump out of your front door, get into your bike or your bus or your car, and get to your destination in, say, 20 minutes? All right. Now, for those of you who know the time it takes you to get to your destinations, how many of you know the distance? How far is it between your front door and that office, that campus you're trying to get to? We don't often try and think about the physical distance separating us. We try and always shortcut and say, well, how long does it take me to get there? If I wanted to see my friend, how long do I need to plan to drive? How long am I going to be commuting? And you don't worry too much about the physical distances. You worry about what time it is to get there. And that's going to be the trick that we're going to try and build up here. How can I use time to measure distances? Inherent in all these assumptions is the speed you're traveling at. Going back towards if you drive on your commute, you'd say you're going 60 miles per hour on the highway. For those of you who prefer the metric system, let's say 100 kilometers an hour. How fast you're going, your speed, correlates to your travel time, and you use that to estimate your distances. So if we're going to try and use a cosmic scale here, if we're going to try and use our time and speeds to measure things on a cosmic scale, let's talk about the fastest speeds humans have ever achieved. If we're going to try and bridge the vast emptiness of space, we need to go very fast. And we're going to talk about the Juno spacecraft. And this is officially the fastest man-made object there ever was. When it was launched, it was sent into this kind of slingshot orbit around the Earth. It was getting this gravitational boost, and it launched its thrusters to escape from Earth's gravitational field. And at its peak, it was going around 40 kilometers a second, which is about 4 times the speed you need to just get away from the Earth. About 4 times faster than any rocket that we've ever launched into orbit around Earth. Juno's mission was to reach Jupiter, one of the nearer planets to us. And Juno was launched in 2011 and took nearly 5 years to get to just Jupiter. Well, that's humanity at its fastest speeds. Alright, a little caveat: if you try and search for online what's the fastest man-made object, you might come across what some dubiously call a manhole cover. And this was a nuclear experiment called Operation Plumb Bob. And to give you just the most briefest explanation of this, we were doing experiments with nuclear bombs underground. And the difference between a bomb and a controlled energy output is the amount of pressure that you have contained in a vessel. If you have too much pressure inside a vessel, you've created a bomb because the vessel ruptures and just throws all this material violently outwards. So when you're doing experiments with nuclear power, you need to control all the pipes where you have all these internal pressures during your experiments. And this possible manhole cover that you'll see references to, turns out that one of the pipes were venting the pressures generated by the nuclear energy, and these experiments failed. It didn't vent properly, and in essence, this manhole cover, it was really a steel plate, had enough energy, enough force pressure behind it that an estimate, physicists calculated, that it could have moved at 101 kilometers a second. Now, we don't really know this value because there is no recording of this thing. The steel plate was just gone due to the failed experiment. And most likely that thing superheated and immediately melted from friction. So while you'll hear references to this for the fastest man-made object, officially it's the Juno spacecraft. One last comment about humans at their attempt to achieve great speeds. one that I just have to squeeze in there because of how fascinating and cool it is what was called Project Orion. And the premise was that we were going to have rockets propelled by nuclear explosions. Put your rocket in space, drop a nuclear behind you, blow it up, and ride the concussion wave forward into space. And this was not just a science fiction idea. We try to build these things. Here's an example of rockets we actually use. You can see the rocket there. And I'll warn you, this was not nuclear explosions. These were basically sticks of dynamite. But here's the proof of concept. You drop an explosion and lift your rocket more and more. This one I'm going to slow down a little bit. And you actually can see the nuclear bomb, the bombs coming up behind it. Let's go back a bit. Watch carefully. There's the bomb. So this rocket would eject a bomb behind it, hopefully have the timing of the explosive set correctly so it doesn't explode immediately inside, but explodes just a little bit outside, and launches the rocket further and further. So, this was a summation of the different things that humans have tried to get things moving really, really fast. And you can imagine that having a nuclear-propelled rocket in space, while sounding truly, absolutely, purely American, is perhaps not the best kind of measuring stick. Because remember the theme we're trying to set up here. How we're going to use time to estimate distances across the universe. And maybe humans aren't the best since we're too obsessed with explosions. So we're going to let nature set the time measurement. Let the universe, physics tells us what we should use for our sticks here. To talk about the cosmic distances, the cosmic scale, we're going to use the travel time of light, the fastest thing in the universe. We can say that light travels at 300,000 kilometers every second. If I was to shoot a laser pointer and have it hit a bunch of mirrors to go across an entire globe, Earth's circumference, remember that, 40,000 kilometers. Light takes a seventh of a second to travel that distance. If I was to just shoot my laser pointer out towards the cosmos and wait a year, well, that light beam in 1 year's worth of time will have traveled 9.46 times 10 to the 15th meters. So one thing to emphasize here is that a light year is not a measurement of time. We describe it in time, but it's a distance measurement. A light year measures distances. And all this is based off of the speed of light, which this is the most common way we're going to write it. We're going to say the speed of light is c, constant. The speed of light c is 3 times 10 to the 8th meters per second. And this is a universal speed limit. If you have matter, protons, electrons, neutrons, if you're composed of atoms, you cannot go the speed of light. This isn't a question of having enough energy, enough nuclear bombs to blow up behind you so that you can ride that pressure wave. It's a matter of physics. There's not enough energy in the entire universe to propel you at the speed of light. Oftentimes I'll get questions about, well, could I use a wormhole to travel great distances that light couldn't in that same amount of time? And to be brief, I'll say that wormholes exploit the ideas of greater dimensions. We as creatures, we like to think in terms of 3 dimensions. We think of a X, we can think of a Y dimension, and a Z direction. So I can go to my right, I can go forward, and if I had a ladder, I could go up. Now, if you want to talk about concepts of, say, a wormhole, I need to start imagining more dimensions. And even drawing it, here's a fourth dimension. It has to be in a different axis. And it's not very clear what the heck I'm drawing, what that means physically. Because we're three-dimensional creatures. We don't think in terms of higher dimensions. So if you're interested trying to think about these problems of these higher dimensional spaces, I'd recommend reading a book called Flatland. This is the story of Square, who lives in a 2D universe. And Square goes on adventures with Sphere that he meets. And Sphere teaches him all about the three-dimensional universe, our dimensional universe. And when Square goes home to tell his family and friends about all the adventures he had in 3D space, they called him insane and a madman. So if you want to think about these kind of concepts of what does it mean to be in extra dimensions, how you are a three-dimensional object, trying to think about four-dimensional or higher dimensional spaces, this is a great way to get started. Continuing to use light as our new meter stick, our new measuring stick. Light from the Earth to the Moon is 1.25 light seconds. Shoot your laser, 1 Mississippi in a little bit, and that light has reached the Moon. Light from the Sun takes about 8 minutes. The light that's shining on you right now, it was radiated from the sun about 8 minutes ago. Light to travel the distances across Neptune's orbit, to travel that entire distance, it'd be about 8.3 light hours. To reach Pluto, a photon on the sun will travel out for 5.5 hours just to reach Pluto. Going to our nearest stellar neighbor, that light takes 4.2 years. Light from our sun takes 4 years to reach our nearest star neighbor. Going back to talking about the Milky Way, that is 100,000 light years across. So imagine you're here on Earth, and let's say you're unfortunate enough to jump into a wormhole and you shot to the other side of the Milky Way. But you did have a laser pointer here, so you could signal out an SOS. Well, you signal out your SOS back to Earth, and it'll take 100,000 years for a signal to reach Earth. It'll take another 100,000 years for Earth to send a signal back to you saying, "We acknowledge you're in trouble." Our nearest galactic neighbor, Andromeda, is 2.5 million light years away. And this is close on a cosmic scale because Andromeda is on a collision course with us. And it's going to take several million years before that collision ever happens. And once again, this is all in a universe that is 13.7 billion years old. And it's much bigger than that distance due to the expansion of the universe. We've talked a decent amount about the cosmic distances. Let's talk about cosmic time. I keep referencing 13.7 billion years old. Let's compress the age of the universe into a 24-hour clock, where at 0 minutes, 0 seconds, the Big Bang happened. The universe was birthed out of that singularity. And at the end of 24 hours, we'll be at 13.7 billion years. And let's look at all the highlights across this clock. About 2 seconds on this scale after the Big Bang, the first atoms start to form. The initial universe was a very hot space. It was a lot of photons and all the hydrogen and some helium in the universe. And those atoms couldn't hold on to electrons. They were just too energetic. But eventually, after that some time had expired, things had cooled off, atoms start to form stably. And once you have atoms of hydrogen, gravity can start to take over and start squeezing them down. And then when you have enough atoms gravitationally stuck together, enough pressure, you start to get fusion, and that's the very definition of a star. A star is defined as an object massive enough to have nuclear fusion occurring in its core. And the first stars start to form around the 10-minute mark in our universal day. After that, it takes a while for us to come around. Anything in this time range, this will be sequences of stars fusing for millions of years or billions of years. We only have 13 billion years to work with, by the way, so we don't have too many generations of stars. Sol itself is probably a second generation star, maybe a third generation. That's the extent. So the solar system forms on this clock around 4 p.m. So the star exists and all the protoplanets that will eventually be the planets are around. Continuing along our clock, around 5:20 p.m. do you get the first life forms. The most basic biochemistry is making single-celled organisms, things complex enough that evolution can start to take over. And when does humanity pop in on this clock? Almost near the end of the day. Humans have been around, in terms of human civilization, only a couple 100,000 years. Our most ancient ancestors, maybe a few million. And that's just, in terms of the atomic day, how old the universe is, the 11th hour at 59 minutes and 58.5 seconds is the only amount of time that humans have been around on this cosmic time scale. We are just a tiny fraction of the age of the universe. And in all probability, we will not live long enough to see the great time that the universe will go off to. Now, as a summation, a quick little summary. Our Phys 103 course, our Intro to Astronomy, that tends to focus on how the solar system form and what happens to the different types of planets. If you remember, you'll have a lot of terrestrial things here and a lot of gaseous guys out here. Why is that? How do you get that? And we'll talk about all the different objects in the solar system. We have a second course, Phys 104, and that's what we colloquially just call our modern astronomy. That's going to focus more on what happens in this time frame, the stars, how they evolve and die, and eventually we'll go into what's beyond the 24th hour, go into the deep, far-flung future of the universe and what's in store for us.